So all they're going to see is this. Okay, right, that wasn't too much effort. You are going to need with you a pen, some paper, and if you're in the room, then come around to the middle desk, please. Right, let's join it from over here. Okay, it's working. I need to turn the sound down here, otherwise it gets really, really weird. Okay, so there you have what we're doing. We're going to look specifically just at bitmapped images. So this is part of COMP1. This is the image section rather than the sound section, but it is the continuation of understanding binary. Okay, let's just have a quick look. Right, okay, so what we're doing is we're going to move on. No, I'm going to have to use this. Okay, so we need to know what our key terms are. And specifically, the key terms for the bitmapped images. You need to understand what a pixel is, what a bitmap is, what resolution of an image and also resolution of a screen. And the main one that we're going to cover today is color depth. Okay. So those, if you're creating your flashcards, those are one of the major things, those 4 things up there, those are what you need to have down there. So what I'm going to do during this session is to then go through each one of these in turn and explain exactly what they are, look at some of the definitions, and I'm going to go through some previous exam questions as well. Now, I apologise if you are online and I don't see your questions. I'm afraid we're having to make use of 3 different computers in order to do the broadcast. I am going as quick as I can. Okay, so can somebody in here define what a pixel actually is?
It's the smallest addressable area of colour.
Absolutely perfect. Almost as if you're reading from the textbook. What we are looking at is it is the smallest area of an image. Now, if you look at the image on your screen, you can see these little black and grey areas. Now, what I've done is I've created a transparency to show you each bit of those bitmaps. And I'm sorry, my computer is going a little bit strange there. There we go. So each one of these here, you can see each little square is essentially a pixel. And it is the smallest area of the image. Each one of those squares in a bitmap can be a different colour. So how many colours can you see in this bitmap in front of you here? You can see 2 colours. Okay, so we have some black and we have white in there. So we have a bitmap image, which has 2 possible colours. And what we need to know is how our computer actually identifies where these images are and what colour they are. So if we move on, what actually is a bitmap? Or a bitmapped image? How would you describe a bitmap image? Go on, Ryan. Where to go? So describe that image in front of you.
Elf.
It is an elf. It's Link, by the way.
Oh yeah, that's not elf. I don't know. The entire image.
Okay, so yeah, we're talking about the entire image. Do you want to add
I
something?
think bitmap is the total number of pixels.
Yeah, so we're looking at total number of pixels. So we're looking at the pixels within that image. And a bitmap, what it does is it uses bits, as in binary numbers, to map our image. So it maps where each of those colours are within a grid. And it's called a bitmap because it uses the bits to actually map out where each of the colours are. So if I move that on a little bit, it is a grid of pixels. And I've put some appalling grammar in there. What I should have said, a grid of pixels in which the position of coloured pixels are mapped within the grid. So that's all we're doing. And in this one here, I'm showing you a bitmap which is incredibly low resolution. I'm showing you something which is a very small image and a very basic image. And the reason I've selected that type of image is it means that you can actually see the individual pixels. Now, if you saw a bigger image with higher resolution, and that's what we're going to move on to next, what would happen to that image? If I made this a lot smaller, what would
Size would be larger.
happen if I made this particularly smaller? It's still got the same number of pixels.
You wouldn't see the individual pixels.
You wouldn't see the individual pixels because actually, the smaller those pixels are, the more difficult it is for us to pick them up. If I put the same size, but I put more pixels, there's more pixel density, what does that mean?
There's a bigger.
Yep, there's a bigger pixels per inch, which means that the pixel density is increased. The size actually hasn't increased. Because the pixels are smaller, they don't look quite so blocky. So what is it called when I make it bigger and those pixels become bigger? Pixelation, yeah. So pixelation is the point at which we can actually see the pixels. Okay, so I've just started to touch on resolution as well. Again, we're talking about resolution, so pixels, pixelation, if you make it bigger, more pixel density means that there's more pixels, but specifically for you, if you are asked about resolution, you're looking at, this is the number of pixels that make up the image. So across here, I would work out how many little squares I can see across this one, and then also how high. So the width times the height actually tells me how many different squares or how many different pixels I have within my image. Now this is all pretty standard stuff up to this point. But the formula I want you to remember is width times height. Width times height, because we're going to start changing it in a second. Okay, I'm just going to get rid of this little thing down here. Okay, so we've got resolution. This also applies to screens. So if you were looking at your monitor, what sort of resolution would you have your screen set at? The rough average.
1080 by
1080
no,
by
1920
1920
by 1080.
by 10, that's quite big.
1080 by 720.
1080 by 720, that's,
Oh, that's quite.
yeah, that's okay.
Oh,
Yeah, so what you're looking at is every time you reset your screen size, you're actually setting the number of pixels on your screen. So now we are using these monitors around here, we're using flat screens. What you are actually doing is you are resetting the resolutions, the number of pixels which are actually being shown. You have a maximum number which these can actually show you. Okay, this is where everybody went cross-eyed. In order to look at a bitmap image, you need to understand that it has width in terms of the number of pixels, it has height, but it also has depth. We have a volume to our bitmap images, and that is to do with the number of colors that we can show. Now here, if we look at this one, color depth, we're saying it's the number of bits used to represent the color of a single pixel. You are still allowed to look a bit cross-eyed at this point because we haven't actually explained what that means. So the color depth is the number of bits for each one of these pixels. Okay. Well, that seems fair enough at this point. We're going to stick with the same image for now. And here we have a color depth of 1 bit, which means that we can represent 2 possible colors. So the image that you've been seeing so far has been a 1-bit color, which means we can either have black or we can have white. And what we do is each color is assigned a bit or a bit pattern. I'm looking at you in that way because you should be writing that one down. Each color has a bit pattern. The bit pattern is then linked to the number of bits. So if it's 1 bit, your bit pattern is 1 bit long. White, in this case, is 0, black, 1. So if this image, and I have counted it, is 32 pixels wide, how many bytes do I need to represent each row of this image? Try and work this one out. If I have to have 1 bit, which has 1 bit per pixel, and it's 32 pixels per row, how many bytes is it? Work it out in pixels, and then convert your pixels, sorry, your bits into bytes. How many bits in a byte? 8. Okay, so two colors, 1 bit. It's full. It is full. Why would it be full? Why would it be full?
You do 32 12 by 8.
Absolutely. That's it. That'll do. Because it's 1 bit per pixel. I'm actually going to skip over that because that says 8 bytes. It's incorrect. It is actually 4. Okay. The next generation of our picture. This is our bitmap. Okay. In our bitmap, it has 2 bits for this color, which means that I can have 4 colors. Why would I have 2 bits in order to represent 4 colors?
Because bytes, there's 2 bytes in 1 bit.
Okay, so if I've got 2 bits, how many different variations can I represent? 4. I can do 0, 0, 0, 1, 1, 0, 1, 1. That's it. I have no more variations. So you can see in here, white is 0, 0, 0, 1, 1, 0, 1, 1. Okay, so that's 2 bits per row, which means how many bytes would I need in order for the row? So each one of these now has 2 bits in it, which means I'm going to have to do what to my pixels? So if I've got 32 across, yeah, so if I've got 32 across, but I have 2 bits, I'm going to have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going up in 2s, which means I've now got 64. Okay, 64, which means that 64, I then need to divide 64 into by what? How many bits in a byte? There are 8, which means I have 8. Is this not getting it, or is this just way too easy?
I'm sort of
Sort of there?
yeah. No.
What you're saying is for every pixel, you have to have 2 bits to represent it. So that instead of where we had 1 before, you're having to have 2. Because I've now got 4 colors. Because each of those pixels could either be white, black, yellow, or green. Now, in order for me to say which one it is, I have to use 2 bits to represent that. Okay. I'm going to skip past this because it's actually, I put 16 and I'm absolutely incorrect with 8. Okay, we've made it even more colourful. It actually looks like a picture now, nearly. This is a 3-bit color, which means I now have 8 colors. How does that work?
2 is part 3.
Think about binary. If I have 1 bit, I can represent 1 and 0. If I have 2 bits, I can represent 1, 2, 3, 4, and 0. Okay? No, I can't. I can represent 1, 2, 3, and 0. I can't do 4 until I get 3 bits. 3 bits, I can go 1, 2, 3, and 0. Because it goes 1, 2, 4, 8. We're still in those powers of 2. Okay, so here I can have 8 colors because I can represent up to a maximum of 7 and 0. 0 is a number. I'm going to do this every week. That's going to be my new catchphrase. 0 is a number. At this point, we've got 8 colors. And what we've used is we've used 0, 0, 0. 0 is a number. 0, 0, 1, 1, 0, 1. Oh, I'm not doing this. You can read it. Okay, so here each of the different colors has a different bit pattern. They all represent ultimately a denary number. Now, if we put them all in a line, what we're going to end up with is every pixel for this one has a bit pattern of 3 bits, which means that I need to now save 3 binary bits for every pixel in my picture that I want to save. Okay, we're going to go right back to the beginning again. We're going to go right back to the beginning again. This is 1-bit color. How many colors can I represent with my 1-bit color? So if you look in your textbook, can somebody tell me which page this is on in your textbook? Harry, I can see your textbook there. What page are we on?
We are on 116 to
116 to 121. Excellent. Okay, so 1-bit color. What we are looking at here is also known as monochrome. Okay, that is one of the things that we will cover. 1 bit, either black or white. There's no grayscale in there at all. It's either black or white. So you can see here, 1 bit allocated to each pixel. We've only got 2 colors there. You could technically get away with having monochrome with 2 other colors, but it wouldn't be monochrome anymore. Okay, 12-bit, direct color. You can see a little bit more in there now. Now, if you look really closely at this picture, which has absolutely been done just for you, you can see little lines next to the dog. So if you look there, it's not quite as clear as I would expect. It's not like I'm looking at you guys. This is not as good as the naked eye. However, it is pretty good. And 12-bit direct color, what we are doing is we are using RGB, which is what?
Red, green, blue.
Red, green, blue. Absolutely. So red, green, blue. And we mix them up and we can make a variety of different colors. And what you can see here is when you get them, if you think back to when we were doing our CSI thing, we were picking up the hexadecimal colors. And the hexadecimal colors are represented here. Let's do a really quick one. FF. F is not 16, 15. Yeah, why is it 15, not 16? It did base 16 because 0 is a number. Okay, yeah, so F is 15. So here you've got FF, which then breaks down into 2 halves of a byte. A half a byte is called a what?
Nibble.
A nibble. Okay, so each one of these hexadecimal letters here, or hexadecimal digits, is a nibble. It represents a nibble. So here, if you look at this, I've got 1, 2, how many bytes for one color?
3.
3. So 3 bytes per color, 3 bytes per pixel in this case. And if you look there, each of the RGB components of the color is given a nibble. So here, it is a 3-byte bit pattern. It's got a long bit pattern. You will certainly never be asked to write one of those in your exam. You would certainly never be given that kind of picture in your exam. More so not with that kind of detail. You never know, you might get an examiner that has more of a sense of humour. And actually, I will show you what they managed to put in there last time. Okay, so here for 12-bit direct colour, we're looking at far more colours, and on top of that, you're looking at the ability to do that red, green, blue mix. That's improved a little bit more. Do you agree? It's actually not in 24-bit true colour. However, that's as good as I could get it on screen. 24-bit true colour tries to represent everything that you can see. So if you, as a human, look at an image, the idea of 24-bit true colour is it represents all of the colours that you as a human can see within your colour spectrum. It should be the best of image that you can look at. What you're looking at here is things, images that you would save, maybe taking this on a high-end DSLR. So for proper big digital cameras, they will try to shoot things in true colour. That means that you've got 16.7 million different colours. Imagine trying to encode it. Imagine the length of the bit pattern that is required if you have 16.7 million different varieties of binary number. So in terms of colour depth, that is why these type of images are massive. When you take those photographs and you take maybe a TIFF file, that is why those are enormous sizes, because what you have is you have this true colour. So what they try and do is they try and represent as many different colours as possible to create all the skin tones, to create the outside tones, to create so everything that you see, making it as realistic as possible. And then we mess it up. And what we do is we say, well, our computers don't work on 24 bits. What size operating systems do you tend to find? Think of Windows 32 and 64. We work in 32-bit operating systems and 64-bit. So what they thought is, well, what we need to do is we'll take our true colour and we'll turn it into 32-bit colour, which means that at the end of this, we've got an extra 8 bits, and we'll play with them. What do you think we can put in it? It's on the board.
Transparency.
Transparency, thank you. We can put transparency in there. So those extra 8 bits allow us to either just cut a hole in our picture or start to create transparency so you can layer things over the top. So when you're playing with Photoshop, what you're doing is you're adding this extra 8 bits on to then create this transparency. Okay. We've seen this before.
That wasn't what I was saying.
No. This was, I think, 2009 exam. But we did this one in class. I've shown you this one. But we're going to go through it again. In the exam, what they've done here is they have shown you each pixel. So how am I going to identify each of these pixels? Yep, they're all in columns, they're in rows, they've got squares around them. They've made it nice and easy. What is the width? 16. Excellent. What is the height of our... Okay, so how are we going to work out the resolution of this picture? 16 times 7. Can you do that for me now? Well, remember, you won't have a calculator in this exam.
137.
Not quite.
112.
112. 112. Yeah, so the resolution essentially at this point is 112. Why is it just flat 112?
There's no,
no depth.
There's no depth to it. There is no depth.
How
So at
do you
this
know
point,
if there's
well,
depth?
you look at the number of colours. Now in the exam, they will only give you a short few number of colours. They won't expect you to do true colour or 16-bit. They will be looking at 1, 2, possibly 3-bit colours.
you said the resolution of an image is width times height.
Width times height.
What can it be width times height times depth?
That's with the colour depth. So that's the memory. Yeah. So that's why I thought I should explain that better. With the depth, it's not the resolution. With the depth, it's then the memory size. To actually get the resolution, it is just width times height. Thank you. Okay, so what they gave us in the exam was this image here, and then you've also got figure 2. Now, figure 2 represents memory locations. Where would you find memory locations? Think COMP2. So year 13 is looking
Main
to
memory.
unpack. Main memory. Main memory is also known as RAM. Okay, so either one, absolutely fine. So this is your memory location in your RAM or your main memory. And what it's saying here is each location is going to hold an 8-bit binary number. So 187, 188, they've given that to you. 200, they've given that to you. So they've been quite kind. If we have a look, why does 0011 work for that image?
Because there's only 2.
That's still where do you see the pattern 0011
Oh, yeah. Is it
on
white,
that
white,
image?
black?
It is. White, black. So, if that is our first nibble there, 1001 takes us up to the middle of the first row, which means that 188 should be what?
If you carry on.
What should it be?
0, 0,
1,
1, 0, 1,
0, 0, which is what's in 188, which is quite useful. So we haven't looked at any of the questions yet, but what we've done is we've just familiarised ourselves with the figures that they've given us. Then they start to do this. Okay, this is where I'm going to have a minor problem, and I'm going to attempt to use the board. It may or may not work. It might work. Okay. So what will be the contents of the location 189? So where are we going to go for 189? Okay. So we're going to look at the second row. I'm just going to attempt to make this into a pen. Make sure my ink colour is actually something you can see. Wish you luck. So we're going to go to the second row. Whereabouts on the second row are we going to get our next byte of data? Okay, so we're going to have what?
0, 0.
Okay, I'm going to try this with a mouse. We're going to have 0, then
0.
Yep.
1, 0.
Oh, that was good.
1.
Where are we?
0.
1, 0.
1, 0.
Okay, so we filled the contents of our memory location there. So what we know about this is it takes how many bytes to fill a row? 2 bytes. Which means if it's asking us for 1 byte, we only need to take half of that row and put it straight in. So it's going to go across, come back to the beginning, then do row 2, then do row 3. So if that comes up in the exam, you know that you can work out what they've given you to start off with and then carry on from there. They might be evil and ask you for 190. So all you need to do is work out where you need to start from. Okay. So we're back here. Now, the next question, and I'm going to change my ink colour for this. the next question on here was, now you've got your binary number, so you had to get that one right first of all in order for this mark. What would the contents be if they are in denary? So what we're having to do is we're going to have to convert from binary to denary. Okay, give it a go. Use your pens.
Is this the right binary value?
So this is the correct, yeah. So we've now got our location from 189. We've turned it into binary. Now we want to know what it is in denary. So don't forget to put your table in. Okay. How have I got to the number 42?
Just add up all the ones.
Add up all the ones. It is the easiest way of doing it. As long as I know that table across the top, I add up all the ones. And at that point, I have to give the examiners a bit of a nod to using 42 in the exam. Well placed. Okay. Then they moved on. This wasn't dependent on what you had before, but still, using that as an example, they then ask, explain how the colour of each pixel is encoded. Now, I've given you a key term for that already today. Have a look at the notes you took right at the beginning. When we looked at how black and white was encoded, and then the black, white, red, no, black, white, green, and yellow. So it's not called colour depth. I gave it a name. So just think about the question just to start off. A bit pattern. Bit pattern. So you could say, and there's a number of different things that they allowed in the mark scheme on that one. You could say each pixel is stored as a binary number. That's perfectly acceptable. Or you could say each pixel is stored as a bit pattern. It's like better. Or each pixel is stored as a pattern of RGB bits, depending on what kind of image that you're looking at. But specifically, each pixel is stored as a binary number or a bit pattern. So that is nice and easy because that's a single bit pattern. If it had more colours, if it had 4 colours, we'd have 2 bits per colour. So that the pattern increases depending on the number of colours you've got. Okay. Did you want to write that one down? Yeah. The answer to that is yes. Okay, now this one will take just a little bit of thought. How many bits are required to store each pixel, so not the whole thing, each pixel for a 256 colour image? So if you had 256 colours, how many bits? It is 8. Okay, why?
8.
Why is it 8? If you said 1 byte, by the way, they'd be okay with that. It's 2 to the power of
8.
2 to the power of 8. Or if you want to think about it as binary numbers, what we could do is we could take the biggest binary number, if we look at that, which is what? If we had all ones, what is that binary number? 255.
Plus 0.
Plus 0 is a number, which means 256. I knew I'd get it in there somewhere. Okay, I'm going to go over those key terms one more time, and then we are done. And we have officially revised.
Yeah.
Okay, so your key terms that you should be able to walk away with. Tell me what a pixel is.
Smallest area of an image.
The smallest area of an image. Fabulous. What is a bitmap?
Oh, God,
Go on, you have it.
The whole grid.
Pixels.
All of the pixels in a grid.
Grid
And it's
pixels, the position.
identified, it's the position.
Yeah.
So they map the
It's gonna
pixels
work.
on an image. The resolution,
The number of pixels that make up the
the number of pixels that make up an image. So what is your formula for that?
width times height.
Width times height,
And the memory is times the depth.
and then color depth
Number of bits.
is the number of bits which is used to represent the color of an image. So we haven't covered the whole of bitmap images in this bit, but what we have done is we've covered all the foundations. What we now need to do, which is just two final things for bitmaps, which is to work out the memory needed to store a bitmap, and we need to go through that formula.
Is that resolution times the color depth?
That's when we start using the color depth. And we also need to look at the way in which we can compress images. But what I'm going to do is I'm going to cover compression once we've also covered vectors as well. Okay, right. Now for people online, I'm going to turn you off. The rest of you, I shall be with you in just a second. Oh, not that one. Proved that we could get online. We should be here. Here we go. Okay. Thank you very much.